Can you imagine the consequences of an autonomous ship losing its power of navigation? Convolutional neural networks have made a huge progress in object detection. Given an input image, an object detector can classify the object and output it with surrounding boxes with high accuracy. However, they can be fooled by adding small noises to the input image which are imperceptible to human eye. As seen here, the ship cannot be detected after the noise addition. Even only one successful attack is very dangerous. When there's an accident in the maritime environment, the crash might cost millions of dollars. More importantly, it can even take human lives. Therefore, more research is required on the attacks, and a corresponding defense system should be found before fully autonomous vehicles starts to be used more commonly.
Traditionally, adversarial attacks in the maritime domain base themselves on a single architecture across the target and the attacker models. When that target model architecture is different, the performance of the attacks drops significantly. This is a term known as transferability. Transferability in terms of adversarial attacks is a new field that is being researched into. Here, the transferability that we're talking about can be visualized in two ways: cross-data transferability and model transferability. Cross-data transferability is when there is an intersection in the datasets of the target model and the surrogate model. Here, the target model is the model which is being attacked, and the surrogate model is the model that the attackers build based on their assumptions. When it comes to model transferability, it is when the surrogate model is based on one object detector architecture, and the target model is based on some other architecture. Also, when the architecture and weights of the target and model is known, it is pretty easy to attack the model. This is called a white box attack because the model detail is known, while the black box attack is when the target model is not known to the attackers and they have to build a surrogate model based on their own assumptions. Our main goal of this project is to measure the performance of a black box adversarial attack in terms of transferability. We aim to clarify this problem of transferability and provide a guiding light to the notion that object detectors can still be attacked even if they are using different architectures and different datasets.
The idea of meta-surrogate performance has been studied extensively. Also, the cross-data transferability is researched. Our proposed approach is using multiple surrogate architectures with cross-data transferability. This is combining these two ideas to make a stronger strategy.
We chose 3 datasets to provide variety: ABA ships, SMD+, and C ships. All of them are publicly available and therefore easily accessible by others. We assume that the datasets have some intersection with other object detection models in the market, and as we increase the dataset intersection, attack is expected to be better. We made superclass mapping to combine them all together. The surrogate model only has the ABA ships, but the target model has all of the 3 datasets. We use 2-dimensional embeddings to visualize the ground truth objects. The coloring and sizing of the scatter plots allows us to discover nature clusters of objects in which visually similar objects are close to each other.
Our experiments contain 2 environments, the attacker and the target. The attacking side has surrogate object detectors of different architectures trained on only one dataset, while the target environment's detector is trained on multiple datasets. For the first set of experiments, we generate adversarial samples from each surrogate model to benchmark how well the MAP reduction of different architectures and datasets transfer to the target model. For the second set of experiments, we train a meta-surrogate model by creating adversarial samples with it, feed it to the surrogate models to generate adversarial losses, and finally, optimizing the weights of meta-surrogate models based on these losses. Once the training is over, we benchmark the MAP reduction on the target model and compare it to the first set of results. Our baseline adversarial attack for these experiments is called TOG, Targeted Objectness Gradient Attack. This family of algorithms exploits specific components of its target's loss function depending on its job. An example here is trying to change the label of the detection to the least likely class. We currently host a Streamlit demo of adversarial attack on EC2 that's available via this QR code. There are currently 2 detection models, the Hoho YOLO V3 and the Abo ships. Our recent model training results have achieved about 75%. Our demo will be available until the end of winter school. If you enjoyed the demo and the video, please leave a like and thank you for listening.